So, as I said, my name is Plana-Riu, and I'm going to present this talk that has for title Enabling Lighter and Faster Simulations with Repeated Matrix Blocks. So, as most likely all of you know, we have two main benchmarks in HPC systems, top 500 and HPCG. While the top one, top 500, is the most well-known one, as it gives the bigger values. Uh, it differs a lot from HPCG, as in our case, we are based on sparse algebra, and given its low arithmetic intensity, we are limited by memory bandwidth instead of peak performance. And then instead of considering this top 500 benchmark, we are closer to HPCG. In order to get closer to this peak performance, which is actually the most performance you can expect from those HPC systems, one possible solution would be increasing arithmetic intensity. In order to see where we are currently, we, as well, you most likely know, we have what is called the roof-line model, in which we divide the codes we have into two different kinds. Memory bound, in which the ones in red in the screen, that they are limited by bandwidth, by memory bandwidth, and compute bound, which is that the codes are limited by the peak performance of the code itself. So, what is arithmetic intensity? We define the arithmetic intensity as the ratio between the number of operations and the amount of data that has to be handled by the code, which means sent or received. So let's have a really small example in which we're going to compare two different cases. One of them is two sparse matrix vector products that we arrange how you can see here in the screen, while we compare it to against one sparse matrix product with two right-hand sides in which we have the same vectors u1 and u2 but arranged differently. What we can see here is that while the two sparse matrix vector products have to send twice the matrix, as we can see in this case, and have to send and receive two vectors and do two operations, the two right-hand side sparse matrix product, we have just one matrix to send or receive, to send in this case, while we have still two vectors to send, two vectors to receive, and two operations to perform. So in the end, that's what I call the equivalent arithmetic intensity, because the proper one, we should take in consideration flops and bytes, not just counting operations and acts of sending and receiving. We can see that the arithmetic intensity of the two SPMM is bigger than the SPMB. So this rings a bell of saying, okay, why don't we try to exploit this in order to increase the arithmetic intensity? As CFD simulations, as we can see here, and as you as well most likely know, are full of SPMBs. For instance, when projecting the vector velocity, usually it's a sparse matrix vector product or something similar that has the same shape but stencil based. Like if we compute the diffusive term, the convective term, or even inside the conjugate gradient, we have some operations, like in this case, that are actually sparse matrix vector products. So if some of those matrix block structures were present in our matrices, then these SPMBs could be translated to SPMMs, and in the end, we could improve the arithmetic intensity and then the performance of our codes. So this can appear under some circumstances, playing with the matrix ordering in symmetries or with repeated geometry patterns. But in this case, we're going to take in consideration ensemble averaging parallel in time simulations, in which what we do is considering one really long simulation. For instance, let's consider, I don't know, a channel flow in which we simulate for all this long simulation, that we can divide it into a transition point in which we start the flow and we let it develop until the statistically steady state. And from that point on, we average those results to obtain the statistics we want to actually obtain. What we do in an ensemble averaging simulation is, instead of running the whole averaging time, we divide it into n times, which being those the n times we're going to run the simulation, while the transition time will run it completely as we need to in the end develop the flow. So once we have that average part, let's say, of our single simulation, small one, we do the average of the average to obtain the statistic that we would obtain originally. This we can see it actually as, okay, we have this, for instance, convective, diffusive, and gradient operators that overall, if we consider the M simulations as a big simulation, behave as a block matrix, all of them, as those operators are pre-multiplied with the canonical product of the identity matrix of order n. So in the end, what we see is that for instance, the momentum equation transforms from the one we all know to one in which those matrices are block matrices, and capital U is and capital P are dense matrices of all of the flows that we are simulating simultaneously. So if those block structures appear, then the SPMBs can be translated into SPMMs, and then increasing the arithmetic intensity. So if in our original case, in the one we usually do, SPMBs have an arithmetic intensity of around 0.16, more or less. So we have this performance. If we increase this arithmetic intensity, in the end, the performance will increase for free, which is actually a nice way of having some speed up. So how can we generate the speed up? This speed up is guaranteed in SPMB, as we said before, because there is this improvement in arithmetic intensity, and then this increases the performance. But how does this translate, or does this even translate to whole simulation and iteration? As we're going to simulate the decision time m times, we need to have a big enough speed up to compensate, to have speed up in the whole simulation, which is actually what we aim for. So this allows us to define what we call the times ratio. That's the ratio between the averaging time and the transition time. That is a key parameter to estimate the simulation speed up, as in the paper from Krasnopolsky in 2018. What he does is basically there's an estimation of the iteration speed up. That's what is now in red. That depends on the number of right-hand sides and the weight of the Poisson solver. And then this is extended to the whole simulation. So this times ratio beta is really important to determine the performance and the behavior of the method. So we have tested this methodology, this block structure methodology, into a differential Hitech cavity of aspect ratio 4 with the basic semi-discrete governing equations that are most likely known without any strange stuff, where we integrate them in time with a third-order Hohenrunge-Kutta scheme with a self-adaptive time-stepping technique filled with air and with a rally of 10 to the power of 10. And then we tested it first in CPUs. We run it in one high memory node of Mare Nostrum 5, consisting of these specifications. We run it in our in-house code TFA with the framework of HPC squared, with 108 OpenMP threads to simulate the whole thing. In this mesh that consists of 400,000 cells per CPU, and as the arithmetic intensity actually depends on the number of non-zeros per row of those sparse matrices, we tested it in 3 different discretizations that we have called 7P, which is this is a 2D representation, so you have to imagine it as there's one in front and one in the back as well. So we have this 7P, then 13P that has 13 non-zeros per row, which there's actually an extension of those in the 3 directions, and 27P, which is, you can imagine it as a Rubik's cube, as well as more heavy, like the heavier PMBs are in the boson solver. We have tested for different number of iterations fixed, and then from 1 to 8 flow states. So those are the results. What we can observe here in between the upper and lower bounds that are set by the ratios of arithmetic intensities is that in 3 cases all of them are in between those bounds, even though the bigger speedups are given by the denser matrices as the amount of data that it's reduced to send it's bigger, so then the bigger speedups are there. But overall, the results are what we expected. Then this translates to a whole iteration as well, and here we can see even more clearly that the number of post iterations is actually important, as what we see there's some difference between 150, 350, and 150 iterations, but we see that the trend is to tend asymptotically to one maximum value. So in the end, more or less, the influence of this won't be that big. So with the results, we can generate a Rootline analysis of this Mare Nostrum code tested in this Mare Nostrum node, in which you see that there's clearly an improvement in performance because there is an improvement of arithmetic intensity. So we are close to the memory bandwidth limit, but what we see is that we improve the arithmetic intensity in all cases, and this improvement in arithmetic intensity generates an improvement of performance. So it's actually what we expected to see. So once we tested this in CPU, then these results were translated into GPUs. So this was running our in-house cluster GPU cluster, using just one GPU, one NVIDIA A100, 80 gigabytes of memory, and was running OpenCL in the OpenCL framework with our in-house code as well in this 21 million mesh. That was the one that was ensuring that the 1-to-1 flow states were filling the memory of this one GPU, and again with the three different discretizations that are here present. So here what we obtain is the results are nice, but it's kind of different because we see that for 7p and 27p the results are actually really nice, fitting inside the both limits really well and what we expected to obtain. While the case of 13p, even though it's in the lower bound, the second case, the results are not that good. So it's something that should be at least considered and reviewed as what's going on here and what can we do to improve. As the generation of good results here and good speedups has been kind of difficult, as loading properly those GPUs has been quite difficult as well. So the results generate this Rootline analysis here, in which we see the same trend as before, even though the results are not that close, except for the 7p to the memory bandwidth limit. What we obtain here is clearly the same trend. We improve the arithmetic intensity of our code, and by improving the arithmetic intensity, what we generate is bigger performances. So that's what we can see here. So eventually we move to the conclusions. So what we have seen here is a method that allows exploiting those repeated block structures that, as detailed before, can appear in different circumstances, for instance, in symmetries or geometry repeated patterns, as some paper has been published from our group. But we took parallel time as an example in this case, as was my line of work. This has been implemented in our in-house code that allows this conversion from SPNB to SPMM without modifying the call of the SPNB product, just adding more right-hand sides to the fields. And this, as shown here, is ready to use in both CPU and GPU architectures, as the results that we obtain are really nice and encouraging, as those results are the ones that we expected. But there are some things that have to be tweaked, as we try to load the GPU as much as possible, and then generate some other issues that have to be considered, and it's something that we're working on currently, and we aim to generate some full LES simulations under this case for future work as well. So yeah, that was everything from my part. So if you have any questions, feel free to ask, and I'll try to answer them as good as possible. Thank you.